We start with the physical system. The simplest atom is hydrogen. It has one proton in the nucleus and one electron bound to it. The proton is much heavier, so in the first picture we keep it almost fixed at the center. The electron is the quantum object we want to describe. The proton creates an attractive Coulomb potential around it. That potential is negative because the electron is bound. So the first physical picture is a proton, an electron, and a potential energy landscape that pulls the electron toward the center. The paper begins from a visual bridge. Imagine the electron motion as circular harmonic motion around the center. This is not the final picture of an electron as a tiny planet. It is a didactic bridge from motion to wave. Take one point moving uniformly around a circle. If we only watch its horizontal shadow, we see a cosine oscillation. If we only watch its vertical shadow, we see a sine oscillation. So circular motion can be decomposed into two harmonic motions. The position of the point is x equals r cosine omega t, y equals r sine omega t. This is the first bridge. A rotating motion becomes two waves. Now comes the quantum step. Instead of describing the electron only as a little dot, we describe its state as a wave. The real part behaves like a cosine. The imaginary part behaves like a sine. Together they form a complex wave. Psi of x and t equals a cosine theta plus I a sine theta. Theta is the phase. In the paper, the phase is omega t minus kx. The symbol k measures how fast the phase changes in space. The symbol omega measures how fast the phase changes in time. Euler's identity compresses the two sinusoidal pieces into one expression. Cosine theta plus I sine theta equals e to the I theta. So the wave becomes psi equals a e to the I theta. This compact form matters because derivatives become simple multipliers. Differentiate the wave with respect to position x. The derivative of the phase gives minus k. So the first spatial derivative is partial psi over partial x equals minus ik psi. Differentiate once more. The second spatial derivative is partial squared psi over partial x squared equals minus k squared psi. This second derivative measures spatial curvature. A short wavelength means large curvature. A long wavelength means small curvature. Now we connect curvature with momentum. De Broglie's relation says p equals h bar k, so k equals p over h bar. Substitute that into the curvature relation. We get minus h bar squared times the second spatial derivative of psi equals p squared times psi. This is the key operator step. Momentum squared becomes a spatial curvature operator. Now use the non-relativistic energy balance for one particle. Total energy equals kinetic energy plus potential energy. E equals p squared over 2m plus v. Apply that energy balance to the wave by multiplying by psi. E psi equals p squared over 2m times psi plus v psi. But we already know how to replace p squared psi. Replace it with minus h bar squared times the second spatial derivative. The result is the one-dimensional teaching version, minus h bar squared over 2m times the second derivative of psi plus v psi equals e psi. This tells us which spatial wave shapes are allowed for a given energy. For the real hydrogen atom, space is three-dimensional. So the second derivative in x becomes the Laplacian. And the potential becomes the Coulomb potential of the proton. That gives the time-independent Schrödinger equation for hydrogen. To let the wave evolve in time, we use the standard stationary state time factor. Capital psi of r and t equals little psi of r times e to the minus iet over h bar. Differentiating this time factor gives ih bar times the time derivative of capital psi equals e times capital psi. Finally, replace E psi with the spatial energy expression. The result is the time-dependent Schrödinger equation. IH bar partial capital psi over partial t equals minus h bar squared over 2m times the Laplacian of capital psi plus v of r times capital psi. The logic is the point. Hydrogen gives the physical system, harmonic motion gives the wave intuition, the wave gives derivatives, derivatives encode momentum, and energy balance becomes the equation of quantum motion.